Okay. So let's get started with part one. I'll quickly go over the write-up and the code, and then if you guys have any questions, uh, you guys can ask me. Make sure your questions are general and not specific bugs. For specific bugs, we have office hours or Piazza. So let's begin. So in homework 4 part 1, we have to create a language model. Uh, I recommend watching the recitation on attention. Uh, this would be very useful for homework for part 1, just understanding what a language model is. Does anyone here want me to explain how a language model works or what a language model is? Uh, so if you guys don't respond, I'll assume the answer is no. And go ahead. Cool. So here we're just building a simple LSTM language model, and you get the Wikipedia corpus with as your data set. It's a bunch of articles. I think what you'd have to do is concatenate. So in this homework, one thing that you have to do that you haven't done probably in other homework part twos is you have to write your own data loader. So that kind of uh, can you see my code right now? Can you see your Jupyter notebook opened?
Yeah.
Okay, so yeah, you have to write a data loader, which where you basically combine the different articles and you create batches of the articles and you send them out. For making the data loader, for writing the data loader, you have to look into uh, iterators in Python and specifically what yield does. uh, that is something that is essential to writing your own data loader. So take a look at what yield does, and a basic overview of the data loader is just that you uh, concatenate all the articles. The input to the language model would be okay. So maybe it's better done with annotations. If I can do that. Yeah. So yeah. So the input to the language model, let's assume that this is our language model, which is basically an LSTM, and my input sentence is I saw a rat. So what we input to the language model would be well, there are a bunch of words before and after it, and let's say you have an input. So you first have to define an input length or a window of text that you input. So let's say that for me is 3. So what I input into the network would be I saw a, and the output I expect from the network is saw a rat. So this is what my target output is. Whatever you get out of the network is something you compare with this and calculate the loss and go on from there. So that's how you have to batch your data set in the language model data loader. The language model has to be some sort of a, let me clear this. So the language model has to be an LSTM and a recurrent model. There are a few techniques you might have to use for achieving the desired results, you might have to use log dropout. This is something I recommend you look at. It's based on it's well, we have a Salesforce implementation for log dropout, and it's based on information about this is given in a in a paper whose name I forgot, but we should have it here in the write up.
I think we also have a Torch NLP implementation of this now. So, I mean,
Okay,
yeah.
yeah, I don't know about that. I haven't used it, but either way, log dropout would be something nice to look at because you would need it in Homework 4 Part 2. So, Torch NLP, you're saying?
Yep. Yeah.
Okay. So, yeah, guys, take a look at the Torch NLP implementation as well. Maybe that might be easier. Uh, yeah, so creating a simple LSTM or try out different kinds of LSTMs, uh, uh, different kinds of regularizations. You might have to use some of these, maybe one or two of these things, maybe more, but definitely take a look at log dropout. That'll help in part two. And there are two tasks you have to do. One task is predicting a single word, and another task is predicting an entire sequence given some length of input sequence. So it's rather straightforward from here. Uh, there's a uh, so we've defined this language model trainer. You just have to define your optimizers, write the training code, and you should be good to go. This test language model uses like you. This is where your understanding of the problem would come in. It's not uh, part one is not too tricky, I'd say. There are a few bugs here and there that you're likely to get, but apart from that, you should be able to go through Homo 4 Part 1 pretty smoothly. Is there anything else in the write up? No. So, I guess for Part 1, this is mostly it. If you guys have any questions, you can let me know.
I just had one question.
Mm-hmm.
So, because we're given like the vocabulary as a file,
Mm-hmm.
do we need to have an embedding layer as part of the model, or it's not necessary?
Uh, sorry. Uh, so, sorry, could you repeat this question?
Yeah, so we're given like these files along with the actual notebook to look up the words and get the corresponding like integer values, basically mapping words or characters to ints. So
Yeah.
because we have this, we don't need embedding uh, the embedding layer in our model, right? Or
No, in general, you do need. So, what's given, you do need an embedding layer of the size of the vocab. So, so isn't it that in the dataset they give like index to words instead of embedding? So, you're talking about like each word is represented by a number, right?
yeah, yeah,
Yeah, but that number needs to be then converted into a vector, which is what the embedding layer does.
I see. Okay.
Yeah, you do need an embedding layer.
Okay. Yep, thank you.
Anything else?
I had some like implementation doubts regarding the regularization techniques, but I'd probably take them up, bring them up in the office hours, right?
Yeah, that probably, yeah.
बराबर मतलब जो प्राइमरी आएगा वो लॉग्स का प्रोसेस करके भेज देता है अभी बस अभी एक इशू ये है कि मैं अभी एक ही क्लाइंट में कर रहा था, तो अभी जब 2 क्लाइंट आता ना, तो कोई तो एक ही क्लाइंट को पूरा मैसेज जाता है, दूसरा जाता नहीं है वो लॉग से।
I think
एक
somebody
क्लाइंट चला है तो चल रहा है सब।
muted themselves.
एक्टिव में एक और झोल है, क्लाइंट साइड पे डुप्लीकेट फिल्टरिंग करना पड़ेगा।
उसका कोड में है मेरे पास।
अच्छा,
Okay, so does anyone have any other questions about 4.1? Cool. So I'll start with 4.2. That's the tricky homework. I'd say it has a lot of moving parts, and that's why it becomes tricky and difficult to catch bugs in. Uh, some obvious things to look at. There are a few corrections that need to be made in the write-up and the code. Uh, I'll quickly open up the code, and this is something. If you have not started, just immediately change these things. I'll also change them in the code that we've given and update it soon. So what we have to do in homework for part 2 is to build an end-to-end speech to text or speech recognition system. What we're using for it is listen, attend, spell, uh, which basically has 2 modules, an encoder which is made up of a pyramidal by LSTM, and a decoder which is pretty much same as the language model that you will build in homework for part 1. So okay. Just going through the write-up, I think it's important to watch the recitation. Which one was it? The recitation on lesson 10 spell. That's essential. That covers a lot of the things that you need for this homework. Even the code is just given there. What uh, we do here is build a pyramidal by LSTM. So I think it's better to look at the code for this homework. I'm assuming a little that you've gone through the recitation and know what the problem statement is. So looking at the code, the first thing that strikes me here is that the letter list that is given to you, so it should be in all small. So all letters should be small. Here the letter list is given as all caps. So the first thing you need to do is convert everything into small letters, because and so on, because that's how the transcripts are given this time. I think this code is from last semester, where the data set that we had transcripts that were in all caps. This time we have transcripts that are small letters. So make that change. The second thing that you should change is this line, the cross entropy loss. Reduction here needs to be none, but it should be given as a string, not as none. The Another issue that is there with the code is in the models folder, which where when the decoder is initialized, it's initialized with it's initialized with zeros. So 0 here corresponds to the index of pad. You have to initialize it with the index that corresponds to the index of SOS, start of sentence. So you probably have to do something like uh, torch dot ones that size one into the index, which is 33, I think. So check that. But yeah, this is what you have to initialize it to and then move it to device. So something like that. This is these are, I think, the major things that need to be corrected. Another thing that needs to be corrected is the comments here, which I think are posted on Piazza. Jacob posted the corrected comments for the forward function. Make sure you check that. And there is another thing that's given in the write-up that's a bit confusing, uh, is handling the variable length inputs. So you pretty much don't need to read any of this 4.1, 4.2. I mean, you can read it. These are different ideas of how you can handle variable length inputs, but you don't need it for the implementation. For the implementation, you just need to use padded sequences, and the cons that they show here are the issues that occur when the sequences in a batch are not sorted. This is an older PyTorch issue that doesn't exist anymore. They've updated it. So all you have to do is make sure that you use enforce sorted. You put in a parameter enforce sorted equal to false. So we have it here. So you don't really have to worry about sorting it. Just put in the parameters enforce sorted equal to false, and whatever sequences you have in a batch are automatically sorted. So you don't need to worry about that. So using just use pack sequence and just put enforce sorted equal to false, and you should be good to go. So don't worry too much about section 4.1. I'll update it. I'll update the write-up and put a new one soon. But what I'll do there is mostly just remove this entire thing and just replace it with 4.1.5 and remove these cons as well. So that's yeah. So that's something you don't need to worry about now. Those were mostly the changes that we found everyone should do, and maybe some bugs here and there. So next, what I think I can do is I can go over the individual parts of the network if some of you have doubts in it, or if you have specific questions of what different parts of the network do, we can do that. And then we can probably look them over in the code as well. So I would begin with seeing if you guys have some questions, and if you guys don't, then I'll go over the different parts of the code. So do you guys have any questions about part 2 or before part 2? Cool. So this is yeah. So I'll just go through the code. This is something I think it's already been done in this recitation. So take a look there as well. What we're doing in the main section is just reading in the data. So reading in the utterances and the text transcript. And these functions, speech to text dataset functions, are defined in the file called data loader. So you have here you have to define a function to load the data. You have to define a function to transform letter to index, which is basically just giving uh, letter to index. Transforms alphabetical input to numerical, replaces each letter by its corresponding. As basically replacing each letter in this sequence with I think it's position, and then you can create a dictionary for letter to index to letter. This is your dataset class, which is again something you use here. Then again, the usual collate functions for train and test batch, that test dataset that was there in homework 3 part 2. So mostly in the main code, this is just loading the data, and in the training loop, you have to write a function train, which is written in train underscore test folder. Go through these steps one by one. Um, huh. You probably don't need set detect. Normally, though, I didn't use it. I mean, like, you don't, if you want to get notices about gradient explosion, this is something we use to clip the gradient so that it doesn't explode. This is something you definitely need. Yeah, basically just go through each of these steps. So uh, set the inputs to device, pass your inputs and lengths. So an issue that comes here is of taking care of the dimensions. Make sure you take care of all your dimensions. And yeah, you probably don't need use dot contiguous, but don't need to use it, but kind of depends on your implementation. Uh, you have to create a mask loss. So what we do in a mask loss is just that here we're using binary cross entropy loss. So the different sequences in a batch have different lengths, and what we want to do, and then they're padded with zeros. So what we want to do is we want to um, not consider the loss for uh, the padding portion. So if I just draw this out, just to show you how the logic for the mass loss would work is that you, let's say you have certain this is, for example, this is a batch. This is the time axis, and this is the number of sequence. So like, for example, the first sequence is has a length of 3. So the rest of the sequence is paired with a bunch of zeros. The second sequence, say, has a length of 2, and the rest of the sequence is paired with zeros. So what you want to do is you want to calculate the loss, but you want, so this is basically what your mask will also look like. So what I mean by creating a mask is this is your mask. It's kind of a Boolean thing where you put a bunch of trues when a bunch of ones where we have a word or a character, and a bunch of zeros where there is just padding, and multiply the mask with the loss, so that the loss for this portion of the output isn't calculated. Uh, this might not be clear if you haven't looked at the homework, but once you go through the write-up, this just using this part will uh, help you generate, or this is basically the logic to write for the mask, write the mask loss and create the mask. So we use criterion to get the loss. So remember, in the criterion, we set reduction equal to none. This is why we, so what happens is the loss isn't summed over this axis towards time. It's not summed over this axis. Usually what you get out of the cross entropy loss is that the loss is summed over the time axis, but it isn't, because we set reduction equal to none, and it's not uh, reduced because we want to set the mask, we want to apply the mask over the loss and then sum it up. So that's how basically you have to use the mask to calculate the mask loss. and then sum it up. Um, and then it's the usual stuff. Calculate the backward pass, take a step to the optimizer, normalize this. I think this is just to calculate the perplexity, maybe. Yeah, but that this is I think the most tricky part here could be is generating the mask correctly, getting the dimensions right. Make sure you get that right, and then it's just pretty much the same thing when you test. When you write the test function. So that was the training and test functions, and then you have uh, models, the models file, which has many components. So I think it's best to look at from bottom up. This is the sequence to sequence. This is the main class in which our model um, is in. So it's simply, as it says, a wrapper model for your encoder and decoder. This model consists of your encoder, which is the pyramidal by LSTM, the decoder, which is a usual language model, and it also has the attention mechanism. The decoder has the attention mechanism, and yeah, so you define the encoder and decoder here, and then in the forward pass, you yeah, depending on if it's you're training or testing, you use them. So uh, yeah, going through the encoder class uses a class called pyramidal by LSTMs. So pyramidal by LSTMs, this class is something that you have to define. Uh, well, the major challenge here is just taking care of the dimensions. That's basically it. Uh, I can go through a little bit of the logic of what happens in the pyramidal by LSTM. So what we do is that the first layer of our bidirectional LSTM, as defined in the encoder, is just a bidirectional LSTM layer. We don't really need we don't really need to change that. Uh, in the next layer, what we want to do is we want to reduce. So this is the time axis. We want to reduce the sequence in time, but we don't want to lose information, as in we don't want to lose the features. So we what we do is, uh, let's say, yeah. So let's say the output of, not considering the batch right now, the output is of uh, the output. So for each time we have a set of features. So let's say the size of the bile STM is S. So at each time instant we have an S dimensional vector. So we have uh, an S into T dimensional output from the first bile STM layer. What we want to do is we want to convert this into a 2S into T by 2 dimensional um, input to the second layer of the LSTM. Uh, yeah. So the challenge here is just that when you uh, do the forward pass, the output of the LSTM layer needs to be converted in a way that it represents what's given in this diagram. Huh. apparently, where's the PVLS team diagram? Wasn't it given in the write-up? Strange. But yeah, you just have to reshape stuff. That's uh, that's the basic idea of uh, the pyramidal wireless team. Reshape the input and just send it through the LSTM layer. Yeah, and I think that's the challenge for that's the only challenge for the encoder. For the decoder, you have uh, a bunch of things going on here. So firstly, you have to use an LSTM cell and not use um, LSTMs. This is because you want to control the LSTM at each time instance, and you want to send in certain outputs, certain inputs. You want to send the output of the LSTM back into the LSTM at the next time instance. Uh, Basically, trying to create this kind of a structure where uh, the output of the first LSTM cell is concatenated with uh, the context and then is sent in. Hmm. So without going into too much detail, I think the most basic thing you can do here is just implement attention. And this code pretty much works as is. As it is said here, just replace values, so this and this with what the context that you get out of attention. And attention is given here. And if you just follow these comments, you should be good to go with attention. Remember, you have to do some kind of masking in attention as well. But yeah, that's just it. So uh, my first suggestion here would be just to implement attention and see where that takes you. You can put in log dropout at certain places, and yeah, so that's basically it. The challenge in this homework is that there are a lot of moving parts here. So you could make an error in the attention or attention module. So there are a lot of places to create a bug, and that's what makes this homework tricky, difficult, and sometimes it's not even like you get an error. It's you the code's working, everything's fine, and but the model is just isn't learning. So make sure you don't make mistakes, which is you know a, not like a real suggestion because nobody tries to make mistakes. But yeah, yeah. So a baseline model to implement would be just implement attention here and get the entire thing working, and from there you can go on adding log dropout, adding teacher forcing, adding tumble noise. Yeah. Yeah. We're doing a character based implementation here, so you don't even think about a word based implementation until you have this model running at least. It's okay if you want to experiment it, but like your first target should be just getting the code running and make sure that it's learning something. Mm, yeah, that's basically everything I thought about discussing. You would probably need teacher forcing, so that's something you cannot get around with. But it's very simple to implement. So once you have everything running, it should not take you too much time to implement teacher forcing. That's basically what I had in mind. Yeah, feel free to ask any questions that you would have. Okay, so that's basically it. I'll stop the recording now, and I'll stay here for like a few more minutes if you guys have okay something in the chat. Okay, yeah, I'll stay here for a few more minutes if you guys have some questions to ask, and otherwise I'll start with my office hours. I'll post the link on Piazza for that.